Welcome to my rather unusual talk. So it's actually about a 60-minute talk that we're going to cram into 40 minutes. So as my grandfather used to say, hold on to your butt. It's a fairly dense topic, but it's an interesting topic. You might not know what probabilistic data structures are. Don't worry. I did a survey. I'll talk about it in the talk, but most developers don't. So you're good. You're in with the majority, the super majority even. So hang on a second. I need to get my slides on so that I can actually control my slides. There we go. Excuse me. So again, my name is Guy Royse. I'm a developer advocate at Redis Labs. The only really relevant information on the slide is my Twitter account, which is where you should follow me because I value my existence based on how many Twitter followers I have. So if you can help me value my existence even more, that would be fantastic. And I want to brag about my 3-letter domain name at guy.dev. I got guy.dev. I mean, how cool is that, right? I have a 3-letter domain. Nobody gets those. So this talk is about 112,092 UFO sightings, and we're going to use them to talk about probabilistic data structures. And so this is a really funny number. It's a big number. It's a surprisingly big number. And it's the number of UFO sightings that are in the National UFO Research Center's database. And a man named Tim Renner actually screen scraped all these and provided the data set on data.world. And there's a link at the end of the talk to these sightings. And they're a delight to read. The data is sort of unsurprising. You've got a summary, which is sort of like a brief description, almost like a title of the sighting. You got a city and state that it occurred in. You've got a date and time. You got the shape of the UFO sighting. So it's is it a disc? Is it a cigar? Is it is it a light? Well, I guess light's a shape. How long it was. There's a link back to the website for the original report. There's the full text, which is really fun. In this case, 3 saucer-shaped ships. That's like Sue sells seashells by the seashore, isn't it? High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation and from time to time seemed to dip down, and they had a bubble-shaped top. And then there's the latitude and longitude of the city where the sighting occurred. So fun data, fun data. And we're going to use this to explore probabilistic data structures. And so I still haven't said what a probabilistic data structure is. And you probably are wondering that if you haven't encountered them before. And when I was putting together this talk, I wanted to get a feel for, how well known are these things? And so I did a super scientific Twitter survey. And my survey said that 58% of developers had never heard of probabilistic data structures. So if you haven't heard of them, you're in good company. 22% had heard the term. So we're at 80% now that either have just only heard it or never heard of them. And odds are good that a certain percentage of that 22% probably heard the term probabilistic data structure in my survey question. Because, we're developers and we sometimes be kind of a literal lot. But we got 4 out of 5 developers that basically have no clue about probabilistic data structures. The other 20% are split fairly evenly between they knew what they were and they had actually used them. So I thought, this is a ripe topic. This is a thing developers, I think, would find interesting and we need to talk about more. So to explain a probabilistic data structure, though, I need to talk about their, I'm going to call them their evil opposite, the deterministic data structure. A deterministic data structure is, it's the data structures you know and love. It's the stuff you've been using since you started programming, right? Lists and sets and arrays and hash tables and trees and stacks and all those things. And the thing that makes them deterministic is that they do what they're told. They are predictable, right? If I put something in an array, I'm going to get it back out. If I put something in a hash table, I'm going to get it back out. Every time, guaranteed. None of this 60% of the time it works every time stuff. It just works. It's deterministic. And we're going to look at one of these deterministic data structures in detail. We're going to look at hash tables. And the reason we're going to look at hash tables is because they use the way they work has elements that are used in a lot of probabilistic data structures. And so this is a good way to sort of get the idea of how the understanding how hash tables work has parallels that are useful. And so we've all used hash tables before. we might call them dictionaries, or we might call them, in Ruby, they're called hashes. In JavaScript, they're everything in JavaScript. I think they're just objects. In Java, we call them maps. But they're all solving the same sort of key value pair problem, right? So here we've got some of our UFO data. We got the city, the state, the date, time, the shape, and the summary of our UFO sighting. And we can just provide the key, and then we get the value. And if we want to add something to the hash table, we give it the key and give it the value, and it adds it. And we can deterministically pull things in and out of this structure. Now, the reason they're called hash tables is because they make use of hash functions. Specifically, they make use of hash functions to determine where to place different objects in the data structure. And so a hash function is something you're probably familiar with. It's something that takes a big pile of data. In this case, we have 6 bytes, which are the UTF-encoded string containing the value Scully. And we have a seed, a big random number that we feed into this algorithm. And then if we provide the data and the same seed, we'll always get the same hash out. And that number is statistically unique. And the data, it doesn't matter how big the data is. We could have 6 bytes, or we could have 6 gigabytes. When we run it through the hashing function, we're going to get a fixed width integer out. This may be a 32 or 64-bit integer. And you might be thinking hash functions. You're like, yeah, I know hash functions, like SHA or MD5. It's like, well, yeah, but no. Those are cryptographic hash functions, and they are intended to be secure, and so they sacrifice performance. They're kind of slow comparatively. Typically, for like a hash table, you're going to use something like maybe a FNV or a murmur hash or something like that. There's other algorithms you can use that generate that same uniqueness but aren't as secure. And so that's the kind of hash functions we're talking about here. A hash table takes those hash functions, and if we want to add something to a hash table here, we've got our hash function, and we've got a seed that we've generated and associated with this hash table. It's not shown on the diagram here. And let's say we want to put the city into the hash table. And so we take the name city, and we run it through this hash function, and then we get a number out. And then we've got an index here, and an array. This index and bucket thing here is an array of all of our buckets. It's actually an array of linked lists. And our array is 10 items wide, or deep, or tall, whatever dimension makes sense here. And so we need to pick a spot in there from that hash. And so what we do is we take the result of that hash and we modulus it with 10. And in this case, we get a 1. And so we put the value of city, the value of Salem for city in index 1. If we want to add another value, we go through the same process. Here, state hashes out and gives us a 4 when we take the number and modulus it with 10. And so we get Oregon in position 4. But sometimes you'll get a collision. And so you get this hash collision where I take shape and I run it through the hash function and I modulate to 10 and I get a 1 again. But there's something there. So I can't replace that. And this is why this is an array of linked lists. Because what we do is the first item in the linked list is the state or the city. And the second item in the linked list now becomes the shape. And so each of these items in the linked list has the key and the value. And so if we run into a duplicate, we just append it to the linked list. And so collisions aren't a problem. We just chain them along. And so doing this process, we can fill up the whole hash table. And here we have Salem, disk. So we got a city, the shape, we got the state, we got the time, and we got the summary or the description. And so when we go to look up city, we reverse that process. And so if we look for city, again, we're going to get the same number and we're going to get the same index out of this hashing and modulus operation happening. And we get position 1. And so we look at index 1 and then we start walking the linked list. And on the first item, we find something that matches city. So we return Salem. If we had instead asked for, say, shape, then it would have walked that list one time and one extra time to get disk out. And then we'll return disk instead. And so this is how a hash table works. And hash table is kind of neat because it makes a trade-off, right? It makes a time and space complexity trade-off, which you do with a lot of probabilistic data structures. You're sacrificing time to get space or space to get time. And so in the case of, say, a linked list, their space complexity is O of n, right? It's as big as the number of items you have. But for a hash table, the space complexity is bigger. It's the size of your index plus all the linked lists. It's a little more complex. But your time complexity to access the hash table is faster, because to access the data in a linked list, you have to walk down the list until you find the item, and so it's O of n. But with a hash table, finding your bucket is O of 1, and then you got to walk that list if there's anything in it. And you want to make your hash table so those chaining doesn't go more than a couple layers in, or your hash table isn't very efficient. It starts acting like a linked list. And so you're making these trade-offs. It's like, do I want to use this structure or this structure because this gives me better performance from a time point of view, and this other one gives me better performance from a space point of view. And in fact, actually, sometimes you're even making these trade-offs within that space. So you're trading out capabilities. So like an array, it just has fixed space. It's the size that you make it. If you need to resize it, well, you can't do it, or you just have to create a new one and copy it. So that's an expensive operation. And so sometimes, but their arrays are super, super fast. Whereas array lists, they have the same space complexity in the sense of how much space it takes, but they're easier to modify. And so you're not necessarily trading time for space in all scenarios. Sometimes you're trading space for space, different types of space capabilities or different types of time capabilities. And there's actually a third thing that you can, a third variable, a third lever that you can pull. And that lever is accuracy. So you can create data structures that have accuracy complexity. And you can say, what if I have a data structure that is super small and super fast, but it lies to me sometimes? It doesn't give me the right information. Sometimes it's not deterministic. It's probabilistic, right? It will say, 0.5% of the time, it'll give you the wrong answer. Is that acceptable? Right? Sometimes it is. If you've got a billion rows because you're an internet scale company, a billion users, and you want to keep track of them in some fashion, maybe 0.5% of inaccuracy is worth it. It can be a good trade-off depending on what you're doing. And so I've got a poor example of a probabilistic data structure to kind of show you what these things look like. And that's where we create a hash table without the chaining. Now, you can see clearly this is probably a bad idea because I put it in the title of the slide. But here we're doing a hash table without the chaining. And so this isn't an index. This isn't an array of linked lists now. It's an array of strings. And so when you go to add city, it puts Salem in position 1 because the hash function spits that out just like before. But when you go to add shape, it gets the same location, and instead of adding it to the list, now it replaces city. Salem's gone. It's deleted. And so if we go back and ask for the city, we're going to get disk back. And so this is a terrible, terrible data structure. You should never do it, but it shows that it's sometimes lies to you. But you get a small performance gain from this because you don't have to walk any linked lists, right? Terrible idea. Don't do it. But it's non-deterministic. And so it's in some senses, a probabilistic data structure. There's another structure that you've used that you're familiar with that sort of highlights this trade-off that you're making. And that is the lowly, the humble, the ubiquitous Jpeg. JPEGs are based on this premise of being a little bit lossy, but good enough. So, some of those blue pixels in this picture of the Devil's Tower, made famous in Close Encounters of the Third Kind. Thank you, Steven Spielberg. Some of these blue pixels are probably the wrong shade of blue because JPEGs compress to the point of losing data. And as it loses that data, it can get smaller, but it doesn't reproduce it with full fidelity. But in this case, we can't see it. And so it's good enough. And so this is the same sort of trade-off you're making with probabilistic data structures. So I'm going to go through some types of probabilistic data structures in a bit, but I'm going to talk about what they tend to be. And a lot of probabilistic data structures tend to be sets that have peculiar properties. Typically a set, like a mathematical set, you can add things to it, you can remove things to it, you can get things from it, you can do unions and intersections and differences, you can check and see if there's membership or count and get the cardinality of it. And so this little set here, for example, is totally not all the icons that are in the Redis logo. Totally not the star, the square, the circle, and the triangle. But, probabilistic data structure might not allow you to remove anything. Maybe you can only add. Maybe you can't do unions and intersections. Maybe you can only do difference, or maybe you can only check membership, but you can't get anything out of it. And so they're like sets, but they don't have all the operations. But they give you great scalability and fast performance, and they tend to be super small. And so some of these attributes that probabilistic data structures will measure are things like membership, right? So you can ask a set, is this thing in the set or not? This is actually a really basic idea, right? And so probabilistic data structures that are optimized around membership will allow you to ask this question. It's a basic question. Is the square in the set? Yes. Yes, it is. Is the pentagram in the set? Did I say pentagram? I meant pentagon. I've been playing too much Dungeons & Dragons. Is the pentagon in the set? No, it's not. Right. So this is a check for membership. Is it there? Yes or no? It's a pretty easy concept. We've got cardinality. And cardinality, and some of you may have some set theory, you know exactly what these things mean, but I think cardinality is a dictionary word for counting things, right? It's just saying how many things are in the set. That's all it's asking. How many unique things are there in this set? And in the case of our sample set here, we've got we've got the square, we've got the star, we got the circle and the triangle. That's 4 things, right? We got 4 things in the set. If we added that pentagon, we would then have 5 things in the set. If we took out the circle, we'd have 3. So we're just counting the number of unique items in the set. Similar to cardinality is frequency. So if we add, say, a triangle to it a second time, well, then we can start tracking frequency. The cardinality doesn't change, but the frequency of the members changes. And so this is counting how many of each thing is in a set. And so there are data structures. Hyperlog is one that works this way. And so what you're doing is you're saying, well, I've got circles, squares, triangles, and stars in my data set. How many in my set? How many of each do I have? And so you can get those counts back. This might be useful for like counting up YouTube videos, how many unique, for this user, how many times have you watched these different videos, that kind of stuff. And so that's frequency. We've got ranking. This asks the question, where does the thing belong in the set? So this is related to frequency. Frequency is actually counting, whereas ranking is throwing away the counting. We don't care how many unique items, how many different items there are for all the items in the set, all the members. But what are their relative order? Give me the top 5 top 4 most frequently used Redis logo shapes, or give me the bottom 3, right? And so we just care about the relative relationship to each other. And then the other thing that we can do, and we're going to look into this one in more detail, is check the similarity of sets. So we take 2 sets and say, how similar are these sets? We're going to do that in a bit with a thing called Jacquard Similarity, where when we look at min hash. And so, and I just have to say, this is my favorite image in all my slide images here. The big heads and the silver suits, it's great. I love it. And even the little glow bands on the wrist just add that extra, fantastic. But for similarity, you're just looking at different sets here, and you're comparing, how similar are them? So maybe some of them have a lot in common. Maybe they have nothing in common. Maybe they have everything in common. So those are the sorts of probabilistic data structures you can have. Here's a list of some choices for these categories, these types of structures. This list has in blue, highlighted in blue, are the ones that I'm going to talk about specifically. And with the little red daggers next to them, those are ones that are included in Redis. And if they got a single dagger, that's in Redis Bloom, which is a module that extends Redis's capabilities. And if it's got a double dagger, it's just in core Redis. Hyperlog is the one there. We've got Bloom filter and Cuckoo filter, which both check for membership. Cuckoo filter is a little more sophisticated. A Bloom filter, you can't remove anything from it, but a Cuckoo filter you can. Hyperlog lets you do cardinality, and it's interesting because it's only 12 bytes long, or 12 kilobytes long, but you can count billions and billions of unique items in it. Count min sketch and count sketch are things that will determine frequency. And then for ranking, we've got Q digest, T digest, heavy keeper, which we're going to look at in detail, and heavy guardians. And these are going to put them in a particular order. And then min hash and sim hash are used for computing document similarity. We're going to go into that one as well, and min hash as well. I did mention Redis modules, and so I would be remiss in my jobs as a developer advocate if I didn't encourage you to go check out all this free software. We've got modules to extend its capability. Go check it out. Bloom filters is the little logo on the far right, but my favorite, honestly, is this one right here. That's for Redis Graph. There's a graph database you can plug into Redis. Graph databases are just cool. So that's been pretty quick so far. Let's go into Bloom filters, and I unfortunately I can't see my little timer bar, so I don't know how I'm doing. Let me scroll up here just to make sure I'm not doing poorly on time. I am doing very poorly on time. So let's take a look at Bloom filters. So a Bloom filter is, of course, part of Redis Bloom. It's actually why it's called Redis Bloom. It's because Bloom filter is the first one we did. And it is a probabilistic data structure that does membership. You can add things to a Bloom filter, and you can test for membership, and that's it. You can't you can't pull the list of the members out. You can't do any intersections or anything like that. You can only check for membership. And when you check for membership, it's going to say, no, this is definitely not in the set, or it'll say, yes, this is probably in the set. It cannot deterministically tell you whether it's in the set or not. It can only say probably. Now, that probably is, I'm 99.5% sure, and so that's acceptable. They have a fixed size, and so when you create a Bloom filter, you're going to say, this Bloom filter is designed to hold 1,000 items. And you don't want to exceed that, because if you do, it'll fill up, and it'll start saying probably for everything. So everything will, it becomes, the number of false positives you get increase dramatically. But they're wicked fast. They got an O of 1 for accessing for checking and for adding. It's the same. And Bloom filters are made up of two main pieces. You've got these hash functions and their seeds, just like a hash table, only we've got 3 of them, not just one. And we have one hash function and 3 seeds, although we could have 3 separate hash functions if we wanted to. It works either way. And we've got these hash functions with these seeds. We're probably going to be computing some indexes with these, aren't we? And then we've got this bit array of a fixed width. And this is how wide, this is how many bits we have to set. And so this Bloom filter, the data that's needed for it is 10 bits and 3 seeds, which are probably 32-bit numbers, probably. And so we're talking bytes here. A real Bloom filter is going to be bigger. It's going to have more seeds, going to be wider. But this fits on my screen and explains the concept. And so those are the 2 parts. And when you go to add something to a Bloom filter, what you do is you take the text. In this case, it's Megatron in the bushes. And this is a UFO sighting that's actually in the data set. These guys who were out in the desert somewhere, I think in New Mexico, pulled off to the side of the road. I'm not sure why, probably because nature was calling. And they're out there and they hear something in the bushes, and they said it sounded like Megatron transforming from the old 80s cartoon. So it's doing that sort of sound that that the Transformers used to make back then. And they got freaked out by it, and they saw some lights in the sky, and they got in their car and took off, and it chased them down the road for 50 miles or something. It's a great story. You should read it. Quite entertaining. But if we want to say, have we seen this story before? We can put it into a Bloom filter, and then we could ask the Bloom filter, have we seen it or not? And it'll say, no, we're probably. So when we put this through here, we get a bunch of numbers, the result of hashing the string Megatron in the bushes. And then we're going to modulus them with the width of our bit array, and we're going to get 3 indexes. So we get 5 and 0 and 6. These are our indexes. And so what we're going to do with those indexes is we're going to set all the indexes that those match to a high. So that now 0, 5, and 6 in the bit array are set to 1 instead of 0. And when we go to read, hey, is Megatron in the bushes in the Bloom filter? We just reverse that. We go through that same process, get those same numbers, and we look and say, are they all 1s? Well, yes, they are. Okay, it's probably in there. We put some other string in there that doesn't return that. It returns some zeros, and we can say, no, it's definitely not in there. And so this is how we add to and read from a Bloom filter. So let's add another value to our Bloom filter here. Let's add, I seen a UFO when I was about 13 years old. This is actually happened here in my hometown of Columbus, Ohio. And what's interesting here is, aside from the bad grammar and the yelly case in the text, which is actually in the original data, we've got a collision. So we get three numbers here. Two of them are different, but one of them is the same as the last time. And so we get a collision, but that's okay. That's why we have multiple hash functions. It means the collision's doesn't going to sink us. It's not going to hurt us. The collision at location 6 is doesn't need to be set to 1, but we set the other two to 1. And if we go in and ask, hey, I've seen a UFO, is it in there or not? We get 1s back. And if we ask if the other one's been seen, the Megatron one, we get 1s back. And so they both still work, and they're not fully overlapped. So we're good. But sometimes you can get a complete collision. Here we have investigators from the Bigfoot Field Researchers Organization observing a glowing green-blue sphere. I hate it when that happens. And we've got, 0, 1, and 6. These are all taken already. And so if we had asked the Bloom filter, is this in here? It would have said probably. But now that we've added it and then retrieved it, it still said probably. So is it a false positive or not? It's kind of weird, actually, if you think about it. It's only a false positive if we haven't added it before. But if we'd added it before, then it's not. But either way, we've got this pattern of bits in our bit array that makes this string come up as probably in the filter. And so this is what's kind of neat, is that the data is gone. We just have these bits. So we don't really know whether we've added it before or not. All we know is that all these bits are set to high already. And so something has added it. And we haven't modified the state of the Bloom filter. And so this is actually why it returns probably, because sometimes you'll get these collisions. But if you get a 0, you know nothing set that. So you can be sure it's definitely a no. And so you get this probably and no. And this is also why when Bloom filters start filling up, they return false positives all the time, because you get this bit array and it's just full of all 1s. And once it's full of all 1s, it's just always going to say probably. Everything is going to hit 1s all the time. So everything's coming up Millhouse, right? So cool. That's how a Bloom filter works. You might be wondering how to determine how wide and how many hash functions to use. And there's some math you can use to do that. And I'm not going to go into this because I want to go a little bit faster. But the math looks scary, but it's actually pretty easy. You just pick a number of items, a number of bits, do the math, and say, is that an acceptable false positive rate? If it is, you're good. If it's not, change the number of bits. And keep doing that until you hone in on it. Or, of course, you can do it the easy way and just use Redis Bloom, which has a command called bf reserve, which will create one for you. And you can just specify your error rate here of 0.5%, and you can specify your capacity of 100. And boom, got a Bloom filter. To use it, we just call bf add or bf mad, and this will add things to your Bloom filter. And to then to check for existence, you call bf exists, and you pass in a string, or you can call m exists for multiple exists, and get multiple answers back. And it will just return a 1 or a 0 if it's found or not. So you can use these very easily in Redis. They're also very easy to code. The link at the end, I have a repo where I've coded this up in JavaScript, and I think C#. So you can check those out. Sorry, there's not a Python version of this, but Python Bloom filter, it's not a complicated structure. You'd be able to bash one of these out really quick. So that's a Bloom filter. Let's look at min hash, and let me check my time here really quick. Apologies for bouncing back and forth like this. I've got about 10 minutes left, so I may not be able to get to top K, but we'll try. If not, the slides are available. Top K is very cool. It's kind of complicated. So min hash is used to determine set similarity between documents. So I've got document A and document B, and I want to say, how similar are these? Have these people been cheating off of each other? And so I'm going to use agents Skulder and Molly here as examples to sort of explain the set similarity here. So Skulder has seen UFOs in California, Nevada, Oregon, Wyoming, New Mexico, and Ohio. Molly has seen them in Florida, Kansas, South Carolina, West Virginia, New Mexico, and Ohio. Area 51 and Hangar 18, right? And so to calculate how similar these sets are, all you do is you take the intersection of the sets, New Mexico and Ohio, get the cardinality of it, and then you take the union and get the cardinality of that, and you divide. And so 2 divided by 10 gives us 20%. These sets are 20% similar. If they had been identical, then you'd get 10 and 10, or 8 and 8, I guess. And they would be 100% similar. And if they were completely separate, they would have the intersection would be 0, and so you'd be 0% similar. And so this is a real simple calculation you can use to compare sets. To compare it with documents, you could make a set out of all the words in a document and then compare all the words to each other. But all you'd really be doing in that case is proving that they're written in English, because we're all using the same words, just not in the same order. And so the way you can solve that problem to compare documents is you can break them into, you can shingle them. You can break them into trigrams and create a set of all the trigrams. And so these trigrams overlap. So we notice 2, and then the next trigram is notice 2R, and then 2R left. And then we go through the whole document until we get all the way to the bottom of a bright glow, and we've taken the document, we notice to our left, further off into the mountains, a bright glow. And we've got a set of trigrams. I suppose you could use tetragrams or pentagrams to do this as well, but statistically, 3 words is usually enough. Unigrams is called a word. That doesn't work. Bigrams doesn't work as well. Everyone's found that 3 kind of is the magic number here. But now we can take this document, and Skolder and Molly, we can compare these sets of trigrams and see how similar they are. Skinner wants to see how similar their reports are. Are they talking about the same encounter, right? And so when we do that, we get a union of 11 and an intersection of 7, which gives us a 0.63 repeating similarity, so 63.6%. So they're fairly similar. Skinner's happy. However, there could be a lot of reports. You could have a lot of documents. You might have hundreds of documents, and these documents may not be short. They might be long. They could be, 100 pages of text. And so these shingles sets of strings gets big. And if you want to compare, say you've got 100 documents and you want to compare all of them to each other, well, the network effect takes over, and you get, that just scales up badly, right? And so what can we do? Well, this is where min-hash comes in. What you do is you take these trigrams and you run each of them through a hash function to get a set of hashed values. And so in the case here on this first hash function, we run every value through it and get this set. And this hash function, we run every value through it and get another set. And so we end up with a set of numbers for each hash function. And then we take the minimum value for each of those sets and create a new set. And so we get a set of numbers equal to the number of hash functions we have. And so we can take, with this technique here, with these 3 hash functions, we can take a document of any size and turn it into 3 numbers. Probably want to use more than that, but we could. And then so we do that with Skolder, and then we do that with Molly, and we get slightly different numbers. And then we can do the Jacquard Similarity calculation with that instead, and we can see we've got here an intersection of 2 and a union of 4, which gives us 50%. Now, 0.636 versus 50% is a fairly big accuracy trade-off, but that's because I only use 3 hash functions. If I was really doing min-hash for production, I would probably use a lot more than that, just to create a more finely resolved signature. And you can save these signatures for future use. So you bring in a document, calculate its min-hash, and save it. And then when new documents come in, you can compare them. And so that's a cool document technique, comparison technique, min-hash, using probabilistic data structures. Our last but not least is top K, which is actually heavy keeper. So top K is a heavy keeper paired with a min heap. And what top K does is it's give me the top K items, right? Give me the top 5 most likely to be used clickbait headlines on, BuzzFeed, right? And so that's what top K does. It ranks. And so it does that with 2 values. We got a min heap and a heavy keeper. And the min heap is just a heap. And in this case, what we're looking at here are words most commonly used in UFO sightings. And so here are our top 5 most commonly used words in UFO sightings so far, and their counts. And so objects of 54, light, dark, sky, disk, these are common words. Usually UFOs are still spotted at night. And so that's our min heap. And then here is our heavy keeper. The heavy keeper's got some parts kind of like that will look familiar. They're kind of like hash tables in a way. But you've got multiple tables. And so we've got a series of hash functions. I have 3 because it fits on the screen. And then we've got a bucket. Each of these tables has an index that's as wide as you want to make it. And each of those buckets in that index contains the hash value and a count. And when we first create these things, it's all nulls and all zeros and just the indexes. So this is a brand new heavy keeper. When it's time to add something to the heavy keeper, let's say we add the string object, we do that same hash function, hash value, and then modules with the width to get a number and index sort of trick again. And here we get 2, 1, and 2. And so we update the appropriate values in here. And so now we store the hash value that we got, and we increment the count by 1. And so now we got 1, 1, 1, right, for these. And if we want to add the value again, well, we find it this time with it's not null, so we don't replace the null. We instead increment the count. And so if we kept adding object, the count would just keep going up. So far we're counting in a complicated way. But if you go to add something else, if you go to query it, you just do the same process, get the same indexes, and then you're like, well, I just take the counts, and yeah, here's my counts. I got 2. Easy peasy. If we add a different value, we will get different indexes. And we have different hashes. And so the first 2 rows here, we just get another location in this array. And so we set them to the appropriate values. But in the last row, we have a collision because the index is the same. But you can see 1352 and 1442 are not the same. And so it can't just increment the count. So what do? Well, what we do in this scenario is we determine whether it should decay or not. What will happen is it'll go down if on a certain probability. And we calculate that probability using a magic number of b to the power of -c, where c is the count. So we've got a value of 2 in there right now, then our c would be 2. And b is a number that's around 1 and greater than 1. So I'm using 1.05 here as sort of a sample. So 1.05 to the power of -2 gives us a 90.7% chance of decay, which is pretty likely. But if that number were really big, say there were 1,000 items in there, that number would be small and it'd be unlikely to decay it. And so this is why it's called heavy keeper, because the bigger that count gets, the less likely it is they'll decay. And so we're going to assume that it decays, and then it decrements it by 1, and it occurred. But when we go to query light, it still works. It just only finds it in 2 rows, not in a third, and that's fine. That still works. And when we go to query it for object, we'll go and we'll get 2 2s and a 1. We just take the max, and it still counts it. And so it's successfully counting it. And so this heavy keeper, they sort of, it's like the numbers are fighting back and forth as things whittle them down and they build up again. Now, this is not a reliable way to count because the numbers are almost always lower than the number that you want. But it is good for ranking because what you can do is as you add things to this list, you can take the count that you got back and you can update the min heap and say, hey, is this thing greater than the smallest thing on this heap? Yes. Swap it out and resort the heap. And boom, you can then ask the heap for the top K. And of course, and I'm getting short on time here, so I'm going to breeze through this. You can do this with Redis. You can call top K reserve. And then it's got commands where you can add shapes to your top K. And commands where you can query it and say, is this item in the top K? Is this in the top 5 most commonly used UFO terms? You can get the counts, which are not super reliable. And then you can just ask for the list of the top 3 or 5 or whatever number of items you have. So that's pretty much what I got. I have a demo, but I know I don't have time for that. So I'm going to skip that. And this is a good little thing full of resources here. This is where I got a lot of my research from. You can check out Bloom filters by example. The Bloom filter calculator does that math for you that I kind of rushed over. A little tutorial on MinHash, a white paper on Heavy Keeper, which is how I learned how to do Heavy Keeper. Here's the UFO Sightings Database. That's the important stuff right there, right? And the new fork, the reporting center for the sightings. Check out redisbloom.io. You can get Redis Bloom. And then one of my peers has an article on Top K on the Redis blog. So go check that out. this is the link to everything. You can get the slides, you can get the links to the code, all that stuff here. So go check that out. The code's in here as well. And that's pretty much all I have. Thanks a lot, and sorry if I went over a little too much, but my name's Guy Royse. Please follow me on Twitter and validate.
Thank you so much, Guy. Let's give Guy a big round of applause. Okay. Okay, just everybody's applauding and cheering for you. Don't worry. Oh, here we go.
Yeah, I got the real screen up now, so. It's a little weird. I can't see everyone, but
So we have.
So it was like rapid fire. I apologize.
It was great.
I'm from the Midwest.
The pacing was excellent. So we've got a few minutes for the Q&A, and if anyone has more questions, please add them to the Q&A tab. The first question is someone is not sure that I understand how you get a value back out if there is a collision. All three values at the same address in a list. How do you choose which one to pick on retrieval if all have the same address?
So is this in regards to top K or in regards to the Bloom filter? If
I
it's
unfortunately didn't
question,
see the time that it was posted.
Yeah. So I'll answer both. So in the case of top K, you've got multiple, in the Bloom filter. So ideally that shouldn't happen. But if it does, then you're still just going to look at, you're going to look at less places. So you could actually get a thing where it comes back 111, 777. We've hit the jackpot, right? And, but then we'll just set that to high. And then when we go to check that, it'll say it's probably in there. So it'll still work. Does that feel janky? Yeah, that totally feels janky. You can mitigate that by making your array wider, and so that's less likely to happen. My rinky-dink example makes it really likely that that'll happen. And so that's the, does that make sense? I think that makes sense. The answer is make it bigger so that doesn't happen. That's really what it boils down to. It could still happen because it's probabilistic, right? So there's no guarantees. I see the practical uses for some of these data structures, and I kind of glossed over that because I was in a hurry. Bloom filters, I think the practical use for a Bloom filter, one I like is, has this username been taken or not? So you're signing up to, say, something that has 1 million users. Select count star from users where username equals name that I want to use is not very scalable. But you can ask a Bloom filter, and it'll say, no, that's not taken. Go ahead and create it. Or it'll say, yeah, that's probably taken, so you can't have that username, Tough Noogies. And if it's not actually in use, then so what? Because that's only going to happen 0.5% of the time, and so that's not that big of a deal. And the user will probably never even know. For top K, one of the really popular uses from it is to count network traffic flow, so you can see where all your heavy traffic is coming from. So you can start shoving packets into it. It doesn't have to be text, and see which IP addresses are hitting you more. For min hash, it's just straight up document comparison. Should I bother to reindex this document or not? Is it different enough for me to bother reindexing it for like a search engine? So that might be a practical use for min hash. So
great. I don't see any other questions.
Any other questions?
Last call for questions.
And for me, I'm going to get alcohol after this. I'm going to say last call for alcohol, right?